Good, and aha, you started the recording for me. Thank you. So welcome everyone to day 2 of our Python workshop. Today we'll be continuing on some of the things we learned last session using a new data set, and we'll get to use some new tools to explore that and create new columns just like we were doing before. But before we get started, we all need to get on the notebook itself. So we're going to access that through Colab again. So I'll go through the process for anyone who doesn't remember, but if you do remember, it's the same process before. I'm going to post the repository link in the chat now. That will be here. So I'll give everyone a second. Go ahead and navigate to the repository and then look on the README that will automatically appear for a blue Open in Colab button. Once you're there, if you right-click or control-click on Mac on the button and then open it in a new tab, you will bring up the Colab screen. Actually, I'm going to go ahead and share my screen for this, just so everyone sees it. So once you've, oh, the meeting controls are in the way, but this is what the repository looks like in the first place. This blue Open in Colab button is what we're looking for first. So then we'll open it in a new tab and we'll bring up a screen like this. So everyone should be here at this point. And if you're ever behind, feel free to just put up a red X in the chat and we'll slow down and we'll make sure you're caught up. But I'm gonna, at this point, once you're here, go ahead and click this 6 notebook DS with Python. So click that and it'll open it up for you. I already have it open, so I'll close that other tab with it open. So now you should be.
Sorry, just a moment. I think we had a red X. Is everyone able to open Google Colab? If you're still having trouble, please feel free to pop up that red X.
Which one is that? I can tell which one I think is Python based you think or something, or no?
I'm sorry, could you repeat the question?
Is it some kind about the Python is it the Python basic review or just the second one?
Look for the one that doesn't have the solutions at the end. So just
okay. I see 6 are here.
Yep. So it should be just called 6-DS with Python, and then there should be nothing at the end. So once you click that, you're in the right place. All right. And thank you for monitoring the X's in the chat. I didn't realize how difficult it was to keep the chat up while you're screen sharing. So I appreciate that very much. All right. So now that we're here, we're ready to begin with this notebook. And we'll be working with a new data set today. So first, everyone can go ahead and run these import statements. That would be great. It will bring up this screen the first time you try to run something. We're going to run anyway because we trust our notebooks. But this will import pandas, which we've been working with. It'll import NumPy, and then Seaborn we're importing to get our new data set. So that if that runs correctly, then you'll have everything you need to work with this notebook. And actually, Dr. Bell, since you're still here, would you like to introduce the data set and what we'll be doing with it, so that I know you wanted to talk more about what we'll be getting into later. So if you don't mind, I think that'd be great.
Sure, that sounds pretty good. So do you want to maybe go ahead and load the data set and just take a look?
Absolutely.
Okay.
So if everyone, to load the data set, we've given this one to you. So if you just run this cell right here, it'll go to Seaborn and it'll load the planets data set that we're looking at now. So before I make Dr. Bell explain a data set that we haven't even looked at yet, let's see if we remember how to at least look at the first couple rows. So does anyone remember what we might do as I figure out how to pull up the chat on while I am screen sharing? Does anyone remember what we might do? Ah, found it. Does anyone remember what we might do to look at just the first 10 rows? Does anyone remember the command for that? So we have our data set. It's stored as planets. That's what we have. So we want to look at just the first 10. Ah, someone's got it. Perfect. Let's do this. That's that. Because my computer is dealing with a lot right now. But here we go. This is what we've got. So it seems we've got some sort of method, a number, an orbital period, mass, a distance, and the year that it was recorded. So now that we have the data set loaded and we looked at it just a little bit, if you'd like to explain, or if you want to just keep going.
Sure, now that looks really good. So we actually are loading the planets data set, as Preston said, from Seaborn. And this is just a data set that comes with Seaborn so that you can play around with it and learn a little bit more about plotting, but we're going to use it to learn a little bit more about pandas. So this is a data set about the discovery of different planets. And so there are different methods that have been used to kind of look at and discover these planets. And as you can see, there are some different columns that have different information about the planets that have been discovered. So we can see that about the planets, there is some information about the orbital period, the mass of the planets. Are we aware of what unit that is? Not quite sure. Probably our resident astrophysicist here can help us figure out what that is. But we also have information about the distance and the year. And so given this data set, we can begin to apply some of the functionality that we have through Pandas and also through Seaborn to be able to make calculations about this, inspect this data set that we have. This data set is more like the data set that you might encounter in real life, where it's not beautiful and perfect. There are NAs, some information is missing. And so in this workshop, we're going to look at what it's like to actually work with a real data set. Preston?
Awesome. Thank you so much.
No problem.
So now that we know about the data set and what we want to do with it, let's start the process of exploring it. Oh, I've got in the chat that someone is showing errors. We will have a bit of a troubleshooting session to catch everyone up later on. So follow along now. Keep in mind that we do have a solutions notebook that if you're having too many errors, you can go to that through the same process that we access this notebook. And that'll help you to keep up, and then you can go back and watch the recording to try to figure out what happened. And thank you for that assistance in the chat. Hopefully we can keep people caught up. But let's look at the things that we might want to explore about this data. So the first thing we might want to know, how large is this data? So this is, to explore this, we will use a function that we actually saw briefly in the previous workshop that you may or may not remember. We only used it just a little bit just to check how many of a certain value is, but it's actually pretty easy to guess. Does anyone have an idea of what property we might want to use to see how large the data is? So we know we have planets, that's what we want. And then we can do dot. We have a lot of things here. We can scroll to look for what we want, but it cuts us off. Does anyone have an idea of what we might want to do to see the size of this data frame? Don't remember, that's fine, because it was only used in one little command line. Length is a good idea, but data frames have both a length and, someone actually remembered it. Look at that. Oh, nope, not size. It's actually shape. And if you started going with size, it would fill in. There you go. You can see shape right there. You can start looking for it. But let's just look at this and see what we get. And I'll show you what dot size does later, but that's also a tool that we do use. But dot shape returns this. So does anyone know what this little tuple is? What do these numbers 10, 35, and 6 represent? Rows and columns, perfect. So this data set is going to have 1,035 rows and 6 columns, perfect. So let's run that planets.size that someone put in the chat earlier and see what we get. We get 6210. Does anyone have an idea of where that number could possibly have come from? And as a hint, I'm going to print these numbers here, rows times columns. Thank you. Yep, that's exactly it. So we can see that if we're trying to explore the size of the data, if we use shape, we can get a rows and columns. But if we use just dot size, it's going to tell us how many individual cells are there in that frame. So that counts every row, every column. Another way you can also explore this, and this is how we used it earlier, but if you can access individual elements of this little tuple. So if you want just the number of rows, you could say planets.shape, just the first one, and then you get the number of rows. So let's look at some more general info about the data. So to do that, what do we think what would be the easiest way? What would be the most easy to think of word to get info about the data? If it was just the first word you think of to get info about the data, what would you think? I'll give you a hint. It's just the word itself. We can just do info. And what this will do, we'll run that. This is going to give us lots of information about the data itself. So what we're going to be interested for this is we have all of this information. So it can be slightly difficult to read, but this is just telling you mostly just the data itself. So if you want specific info, so let's get info about, oh, that's an interesting fact. So if you didn't read that in the chat, Adam said the masses are likely, the unit is the mass of Jupiter, which is how they express the masses of exoplanets. That's interesting. I didn't know about that. But let's look at the null counts and see what this does. So here you can see we have a very different output than what we got before. And this is going to return a short list of the non-null count in each column of the data frame. So you can see in method 1035, we remember that 1035 was the total number of rows. So we know that method, everything has a value. For number, everything has a value. But we can see for orbital period, there's a few that don't. And then for mass, more than half of them don't. So this is something that you will likely run into when you're working with real data, is that it's not always in the exact condition that you want. So this is something that's always helpful to know, because think about it. How many operations that we were learning about in the previous workshop did we try to do that would have gotten interrupted by an NA value? Take the average of 2, 3, and nothing? Not 0, but just NA? Impossible to do. So it's always good to know how many NA values you're working with, because in that example, if you were taking if you had 1,000 twos and then one NA value, it's pretty okay to just think about drop the NA value and then say that the average of that column is 2. But if you had 1,000 NA values and 1, 2, it doesn't make much sense to drop the NA values and then still say the average of that column is 2. Because in reality, who knows what the average of that column was, because almost every value was NA. So this is a helpful tool to make sure that we know about how many NA columns we're working with. Now, if you don't want quite this much info, you can also get an abridged version of the info. So let's do planets.info, and let's say verbose equals false. And see, this is going to give us about the same info that the size gave us and that it gives us the range. We have 1035 entries, gives us the number of columns, but this also will give us the data types of the columns themselves. So you can see we have 3 float columns, 2 int columns, and 1 that's an object. And then it also tells us the memory usage if we need to know that. So let's look at some other things we can use to learn more about the data set. There's another function that you may want to use called describe. And we don't need any arguments for this one. So let's look at what this one does. So you can kind of see what's going on here. Does anyone know what all of these numbers might mean? Count, pretty easy to understand. This is going to tell you the number of values that aren't NA. As you can see, it lines up with the number of non-NA values we had before. So for number and year, you can see that all the values are there, but for some of them they aren't, especially mass is almost completely empty. But this is helpful because it also gives us the mean values, the standard deviations, the minimums, the different quantiles, and the max. So this can be helpful when you're initially exploring your data set to learn more about each column, because this will give you all of these numbers for every column so that you know exactly what you're working with and kind of what bounds all of your data falls within. So next, let's look at another way to count the NA values. We can see every time here, we've counted the values that are not NA. But let's say we wanted to count the values that are NA. So we'll start out, we're working with planets again. And we have a function. Maybe I can scroll down and find it, see if it doesn't cut off. Is NA, there it is. So what do you think would happen if we just return this? Does anyone know what this is? Take a guess on what it did when we just said is NA. Yep, that's right. It's a logical operator. All it does is go through that our whole data set and tell us if something is NA or it isn't. So this one, we had a value, so it's not NA. This one didn't have a value, it is NA. But if we're trying to count, that doesn't really help us. So what do we want to do now to figure out how many of those values were NA? We'll add another thing here and see what we want to do next. So what we're going to want to do next is we're going to sum these values here. But there's something we have to keep in mind with sum. Sum doesn't usually like to count NA values, because think about it, when you're adding 1 plus 2 plus 3, that's easy, it's 6, but if you do 1 plus 2 plus 3 plus NA, then you don't know what to do. So by default, sum likes to skip that. So what we have to give it is this skip NA equals false. And now it knows to count the NA values. So let's run that and see what we've got out here is a count of the NA values in each column. So this is a super helpful tool to be able to count exactly how many NAs we have. And you can do a quick sanity check here. So you can compare this up against the count from up here. And you can see that each time the count of a column plus the count, the number here, is equal to the total number of columns, 1035. So obviously 1035 plus 0 is, but then this 992 plus 43 is also equal to the total number of columns. So that helps you know that you're doing the right thing. Where did I skip down to? All right. So now let's look at getting the column names. Now, what do we think we might want to do to get the columns? If you're here, yep, it should pop up for you. And maybe you can scroll and find exactly, you've already got it, planets.columns. So that is there. And this is just going to return this index, and then it tells you the name of each column, and then it says dtype equals object. So that's just going to tell you that it created an object with each of the column names in a list like this. So that can be helpful if you have a very large data set. Imagine there's a scroll bar here. You have hundreds of columns and you don't want to scroll all the way over, but they can be helpfully listed right here pretty easily. So let's look at the value counts for the categorical data next. So before we look at the categorical data, we should first make sure we define that, just in case anyone hasn't worked with this before. So categorical data means that the values in that column are measuring one category. So the example we have here is the method. So there are a few different methods, method 1, method 2, and so on and so on. But you're never going to have method 1.76. That doesn't make much sense because there's only certain numbers of methods. So that's what we mean by category. So since we know category or method is our categorical variable, first we want to just access that column. So if we're going to just access that column, we'll do that like this. That's the dictionary method of accessing just a single column. And then we want to know how much of each value there is, what number. And intuitively, the word that we might think of is the exact word that works. So let's use value counts. Oops. And there we go. So here we can see the methods each have names. There's radial velocity, transit, imaging, microlensing. So this is the method that was used to record each of the values that are in our data set. So we can see 553 of them were recorded using radial velocity, 38 through imaging, 23 through microlensing, and so on and so forth. So this can be really helpful when you're looking at large data sets that have specific categories and you'd like to know if your data set is mostly comprised of one category or just the general makeup of how each one is distributed. So there's one last thing we'll look at in data exploration, and that is the value counts for all of the columns. That is done. This is a bit of a longer function, so stick with me and I'll explain it at the end. So we're going to start out with this. Now, if you attended our first series of Python workshops, or you have experience with Python coding in general, you'll recognize that this means we're starting with a list. And what we're actually going to do here is called a list comprehension. And if you're not familiar with that, then just follow along here and I'll type everything out and then I'll explain kind of what happened at the end. So first, we want planets. We want the value counts because we want the value count for all of the columns. And then we're going to do 4. Okay, so we'll start with this. So this is going to be our first introduction to a for loop. It's the first introduction for you, or you may kind of understand what's going on here. But if not, this is going to say for each in planets.columns, and we know what that returns. It's back up here. It's going to say for each one in this list of 6 columns, it's going to do planets.value counts for each one. So we want to know. So let's run that and see what it does. Oh, we've got an error. So some of them are not going to be able to, some of these in here are not going to be able to get value counts. So let's try to think of how that is and go back to the original data set. So look at these columns and try to figure out why you couldn't get value counts. Why do you guys think that getting value counts for some of these columns doesn't make sense? It's a bit of a difficult question, so. I coded values counts. That would be something, wouldn't it? Ooh. Well, look at that. All this runs, this is going to take a second. I'll explain why. That's a good catch. But let's go back to our original data set. If we're getting value counts, let's just look at this mass column. What does it mean to get value counts? It means we'll see how many values are exactly 7.10 and 2.21 and 2.26. That doesn't really make much sense. Why would we need to know exactly how many values were of that exact mass? Really, we only want to see value counts for columns like the year, where it's a little bit more set, or the method or the number. So this is going to take quite a while to run. So let's see if we can stop that. But the way to prevent this is we can add an if here. And then we only want it to run if the column, so let's say planets X, and that's going to give us just the column, and then dot dtype, which will give us the type that's in the column, and we want that to be an object. Now it's going to be sort of not run that column, because if you, what it's trying to do right now, why it's taking so long, is it's trying to give us values for every single individual little mass. And you can see why that would be not a very good idea. So let's see if Colab allows us to stop it. Interrupt execution. Let's try that. It is not very happy with us running that. So this is why you have to be careful with things like this. But luckily, we still have Colab pulled up. The notebook is the same. So hopefully you didn't run that. If you did, you can just go right back here. And this is what it's supposed to, oh, I'm gonna have to rerun the data set. This is what it's supposed to look like when you've done that. So you might say, well, what's the difference between what we did? Yeah, this is going to be, so you might say, what's the difference between what we did here and what we did here? Looks like the same output. And that's because it is the same output, because we only have one column where the data type is an object. So now let's look at how we might want to handle the missing values. So this column is almost provided, but what we're going to do here is we're going to create a new data frame where we just get rid of all the NAs. Like, let's decide the way we want to get rid of NAs is we're just going to drop them. We don't want to deal with them at all. So let's just get rid of them. So the way to drop NAs is intuitive again, drop NA. The only thing you have to do here, it brings up an axis parameter. So do we want to drop the rows or do we want to drop the columns? And what do you guys think? Do we want to drop rows that have NAs or do we want to drop the columns that have NAs? Exactly, we want to drop the rows. If we drop the columns that have NAs, suddenly we've just dropped half of our data set away because only 2 of them didn't have any NAs. So we want to retain all the values that are complete. We just don't want to keep the rows that are incomplete. So let's give it axis equals 0. What that's going to do is drop just the rows that contain incomplete data. So now we have 2 different data frames, right? This one is called test, and it will not contain any NAs. And then this one is called planets, and it will contain them. So let's run this and see what we get. All right, so this length function here is going to tell us the number of rows in each of the data sets. So what we've done here is we've printed number of rows in the test data frame is 498, and the number of rows in the original data frame is 1035. And that makes sense because if we go back to our list of NA values, we remember that the mass column had exactly 498 values. So that was all we could keep. We couldn't keep anything that didn't have the mass. So now we're down to less than half the data set. Sometimes that's okay, but it's always important to keep in mind exactly how much you're losing when you just drop NA. So you have to make sure that you're taking everything into account when you do that. So there are a couple other ways to deal with missing data except for just dropping it. So here's a method of filling the missing values with just the mean.
Hey, Preston.
Yep.
I just wanted to make a very small note. In the above thing, you can also pass, instead of passing axis equals 0, you might have covered this in the previous session, but you can pass axis equals rows in quotes in case you forget. So
let's try that out. Let's just demonstrate that. Look at that, it returns the same thing. So if you're one of those people, and that is definitely something that I do, people can't remember 0 the rows or 0 the columns, and it's difficult to think, and I don't want to end up dropping half my data set, you can just make it simpler on yourself and type axis equals rows. And that's a really good tip because it definitely can be difficult to remember exactly what you're supposed to be dropping here. So thanks for jumping in there. So let's get back to looking at what we wanted to do if instead of dropping the NAs, we just wanted to replace them with something that's about what we wanted. So to do that, let's create a new data frame, and we're going to call this minutes equals. Make sure I can spell. All right. So we had the function drop NA if we wanted to get rid of them. What do I think we might want to do if we wanted to fill them with something? Close. Fill NA. Yep. Look at that. The command is right there, just as you'd expect it to be. Now, fill NA is different than drop NA because drop is easy. If you tell it to drop something, it knows what to drop. But if you tell it to fill, it doesn't necessarily know what to fill it with. So we'll have to give it a value to fill it with. You can see the parameter it needs is a value, and this underline means it needs that or it's not going to know what to do. So what value do we want to give? Now, for this demonstration, the value that we want is just the mean. So we're going to find the mean of that column and we're going to put it in. And the reason you might want to do that is because that way it won't throw off any calculations of the mean that we might do in the future. Because if you're averaging in what's already the average, then you're not changing anything. So that can be a way to make sure you still have the values without interrupting your calculations of the mean. So let's just use planets.mean and see what it does. And we note this is creating a new data frame. So we're not going to see anything when this creates. It's just going to, boom, it's created. Now let's see if we have any new values. This is our planets. That's our new data frame. Now let's see, do we remember the command to check if there are any null values, just like we did above. It's a two-step process. The first step is null. And we'll remember that that will just give us the logical operator that'll create a new data frame that'll just have true or false values. Was this null or was it not? And then we want to sum that up. So we'll do that. And look at this. All of them are zeros. That's what we like to see. Because that means that now we have filled all our NA values with whatever the mean is. So actually, let's look at that to see if we can look at any of the NA values. I'm going to add a code block in right here. And we're going to do imp planets. And if we remember, there weren't any NA values originally at the top, but there were some at the bottom. So if I wanted to look at the last 10 rows of the data set, how would I do that right now? Does anyone remember the command? Tail, yes. Let's do tail 10. And we can see a lot of these for the mass that were in A are now filled in with this value 2.638161. So we can see that it worked out. And we can also see that the orbital period, the likely mean there was filled in too, unless both of these are 2002.91767596. So we can see that it's done a good job of filling in the average value whenever we had an NA value. So the other option is just to drop the NA values like we did before. So let's look at that. We already see that it's filled in called drop planet, so we use that as the name of our new data frame. Let's go back to that drop equals planets. We're dropping again, so we're using that same command before drop NA. What else do we have to add here? Do you guys remember? Fill in the axis. And like Adam said, I'm going to continue to do that. Just type in rows there because that's much easier. And then what we're also going to do is this command, and I'm going to type it first, and then I'll tell you what it does. So drop planets. I'm going to reset the index in place equals true and drop equals. All right, so we're going to run both of those, and we can see that the number of rows in the original data frame is again the 498 value. So let's say I don't have this and I run this. Is it going to get the same thing? It will. So I'm going to show you what happened here. So let's look at drop planets. And we'll look at the first 10, let's say. That wasn't a good, should have looked at the last 10 because it doesn't drop any of these. So let's do tail. Well, it drops all of those. So maybe it'll be difficult to demonstrate this. Ah, no, this will show it perfectly. All right, so this is the index over here. Can you see what it's doing here? It's counting the old index from planets. So we have 633, 34, 36, 37, we skipped 35, and then here we skip all the way to 784. So we can see that it dropped the values, but it didn't reset the index. So if I was wanting to access this row, we know there's only 498 rows, but if I try to access row number 498, it's not going to give me the last row. So we want to make sure that we still are resetting the index. So that's what this function right here is going to do. You're going to have drop planets.reset index, and then these two parameters will basically just let it know what you did. So what we did was drop. So we set drop equals true, and then in place, it means it's creating the same, it's just fixing the data frame instead of creating it. Let's run that instead. We'll see we got the same number of original rows. Now, if we run this, look at the end. Oh, now it's exactly fixed how we might want it to be. So there's 498, they're numbered from 0 to 497. And now, if we wanted to access the last one with 497, then it would be able to actually, we would be actually able to get the row that we wanted to get. So that's a way, that's something that it's good practice to do to make sure that you can always access the data frame in a way that you're expecting to be able to, and that others could access the data frame in a way that they expect to after, if they're working on your work. So it's really good for collaboration to make sure that you're not leaving the data frame with a bunch of strange indexes that no one knows how you got. So finally here, let's make sure that there are no null values hidden in there. So we can see we saw the top 10 and there weren't any null values, and we saw the bottom 10, but let's just make sure. So one more time, let's look at the number of null values. So we'll say drop planets, that's our data frame here. Dot is null. Dot sum. Do skip NA equals false again. And we'll make sure that, perfect. We have no NA values. So now we know that we have a data frame that we can work with without any NA values. The index is good. So we've created something that we can work on now and feel confident in. So let's move on to the next topic. Next, we're going to look at selecting data from the data frame, which for those of you who attended the first session is something you probably already know how to do. So with that being said, we're going to quickly go through this section and see, just make sure that we remember how to do it. So does anyone remember how to just get the method column? And any of the methods that we learned to do this will work. And if you weren't in the first session, don't worry, we'll go over it still. Just I'll wait for anyone who may have the answer and we'll talk about it. So does anyone remember how to select just one column? You can just type the code in the chat if you'd like. All right. Let's work with imp planets again, that's fine. And then just the method call. So we're typing method. Let's look at that. Let's see what we get. And look at that. We've got just the index and the method call. And I appreciate you not using not telling me to use one of the data frames that we had dropped things from. So that's good. So next, this says try it yourself, but we're going to go over this one together. And then if we get to the one in mutate will actually open breakout rooms. But let's go through these together. So the first thing that we want to go through here as a review is we want to get everything other than the orbital period column and display the first 10 rows. Does anyone have an idea of the first step that we might want to do here? So don't worry about getting just the first 10 rows yet. How would we get everything from the columns that are not the orbital period column? And we'll start with imp planets again, that's fine. So of the three methods, there's the dictionary method of getting to columns, there's loc, and there's iloc. Does anyone know which one they might want to use here? If you have code, feel free to post it, or I'll just walk through it slowly and give hints. If you want to jump in with the rest of it at any point, feel free to just drop it in the chat. So my suggestion is here, we're going to use loc. And the format for that is we'll open brackets after that. So we want everything from, it says we want everything other than the period column, but we want the whole column. So how do we get everything from a column? What's the first thing? Does anyone remember the character that'll get everything from a column? Perfect, there we go. Yes, I like to see it. All right, so we'll do that first. That'll be the first argument we need. And then we want everything except the orbital period column. Does anyone have any ideas on how we might do that? So here, the next argument, we're telling it which columns to pick from. We're giving it a set of columns that it can look through. So if we do something like this, dot columns, and that would give every column. We want every column except for one. We don't want it if it's the orbital period column. So does anyone have any idea how we might do this? So if we want, let's say we wanted to get just the orbital period column. We could say if the column is equal to orbital period. So that would give us just, we can run that now. And this gives us just the orbital period column, but we want everything but this. So how can we change this to, instead of giving just this, we want everything but this? Is there anything we can change with the operator here? Feel free to jump in the chat or just unmute yourself and say it if you'd like. Ah, look at that. So let's try that. Let's do exclamation point equals. So yeah. Oh, look at that. Everything except that. So if you're unfamiliar, this exclamation point equals means not equals. So now we're saying we want the columns that are not equal to orbital period. So good. So now the last step is to display just the first 10 rows. So does anyone remember just the first 10 rows? We've done it a few times already. That's going to be dot 10. Easy as that. And there we go. We have just rows 0 through 9. We have the exact ones we want. And that's how you get that. So now it wants us to use dot iloc to retrieve just the last 2 columns. So I'll give everyone just a second. If you were in the last workshop, see if you can kind of come up to the answer with the answer to this one. If not, just sit back. We'll talk through the answer when we get there. That's a challenge to just see if you remember how you might do this one using iloc. And once you have your answer, I'll give you the first part. Feel free to post it in the chat. All right. So does anyone have the answer to how we might get just the last two columns using .iloc? So the first thing we want to do here is we want to get everything from the columns. So like we said before, to get everything from the columns, we'll just use a colon like this. And now we want just the last two columns. So there are two different ways to do this. If we remember, there are 6 columns here. So you can either say you want 4 through the end, or you could also say you want -2 through the end. Either of those will give you the same thing. But if we run this, we'll see we have just distance and year, which were the last 2 columns. And now let's look at the last one here, which is use .loc to get the orbital period through distance slices, and then use iloc to do the same. So we're working with IMP planets again. So the first one we know to use .loc, gave that to us. We know we want the whole column. This time we want the orbital period through distance. So we know we're giving it something here. Does anyone know what goes on either side of this? The selected columns that we want. That's right. So the first one we wanted was orbital period. And the second one we wanted is the distance. And if we run that, there we go. That gives us the slice. So it also gave us mass in between. So you can see there that it's just as valid to put the names of the columns on either side of the colon using .loc. Now we can do the same thing with iloc. We just have to remember the actual index of the columns. So does anyone know what the actual index of these columns, what we should put here to get this same data frame that we got? What goes on either side? So let's go back to the original data frame and look at it. Actually, since that's really far up, what we're going to do, we can just look at it here. Planets, let's just look at the first few. So here's our data frame again. So we know we want orbital period through the distance. So if we consider the index here, we know this is 0, this is 1, 2, 3, 4, and 5. So now we want it to start at 2, and then we want 3 and 4, and then we don't want 5. So you want to start at 2, and then get 3 and 4, and then don't include 5. And with this, it'll return the exact same data frame that we want. So that is a quick review of selecting columns using lock and ilock like we did before. Oh, Dr. Bell, I see you're back. Would you like me to keep going to filter and mutate, and you can take over where you were wanting to?
Sure, that sounds great.
All right. So next, let's do another filtering, which we covered right at the end. So we have a question here. What methods do we have to filter rows? There were 2 that we went over in the last workshop. So if you were here, what methods do you remember to be able to do that? Go ahead and post your answers in the chat if you remember either of the methods that we have to filter our data set. So if we were wanting to do this, what entries have mass greater than 10? What are the 2 ways that we could do that? Query, that is right. That is definitely one of them. So we'll put there. And then what was the first one? Lock. Yes, we can use lock and ilock to do that as well. So we'll start with that one because that's the order we went in last time. So let's look at how we might want to do that. I'll get rid of this so it doesn't throw errors when I try to run it. So does anyone remember how we do this? So we know we're working on this same data frame again, and we're using this to try to filter it. Does anyone remember the formatting here? As a hint, remember in these up here, we were selecting everything from the rows, but now we don't necessarily want everything from the rows. We want only the rows that fit this condition. So what do we want to put in the first argument? Good, that's the right start. So we're looking at our data frame again. But if we did this, what's it going to give us? It's going to do everything again. So we want to make sure that we're filtering a certain thing here. Ah, look at that. You got the rest of it. Perfect. Thank you. So let's type all that in and see what it does. Mass, and then you want the greater than 10 outside like this. And then what do we think we should? Perfect. Look at you on top of it. So let's run that and see what it gets. And look at that. We have all the masses that are greater than 10. We can see it's certainly popped off quite a few rows, jumps from 8 to 63. But this is all of the rows with the mass greater than 10. And now that we figured out how to do it the longer way, let's see if we can use query to make it look simpler. Let's look at our data frame again. Let's use query this time. Do you remember how this one works? What do we put inside the parentheses here? You can kind of see it brought it up, the query string to evaluate. So what's the formatting there? What should I put inside these parentheses? You know it's a string, so we can start out with just these quotes. And let's put that inside the quotes and see what it does. Mass greater than 10. And look at that. It's returning the same data frame with all the masses greater than 10. So that is a review of how we filter that. This next one is basically the same things. We'll see if we can use a query here just to see how it works. Make sure we're getting good practice. So this one, we want entries with orbital periods greater than 1,000. And then we want to know what years they were discovered. So let's just try to use query here. Does anyone have any ideas on what we might do here? We can start by breaking this into parts. So if we were going to use query just to get orbital periods greater than 1,000, how would we do that? What would we put in here? So just like before, we're going to go ahead and put in orbital period. And what are we going to get out here? This is our same data frame as before, with all the orbital periods that are greater than 1,000. And now, since this is a data frame, and we want just the years, we want just one column of this data frame, we can access that just like we've been doing with any other methods of just getting one column. The simplest one is just the dictionary method of just doing year. Just get the year on the end. And there we go. Now we have just the years. It's the same length as the data frame we had before. If we want to verify that, we can take a year back out, look at the whole data frame again, see that it's 208 rows. If we want just the year, we have a length 208. We have all the years we want. So now, the last thing we're going to look at with kind of combining our select and filter commands, we're going to mutate. And if you were here for our workshops, you'll recognize mutate as creating new columns based on the ones we have. But if not, mutate is the word that we use for changing the columns or creating new columns based on the data we have in our data frame. So let's create a new column now, and we want to create a decade column. So I'm going to show you how this works. We want to create a column called decade. So the first thing we're going to do, dictionary-like indexing. So we just say imp planets decade. We're creating a new one. Decade doesn't exist yet, but we can make it exist just like this. And then we want to decide what we want decade to be. Now we're going to use a cool math trick here to actually get the decades, but I'll show you how we're using the data in the data frame to do this. So we're going to start out by doing 10 times imp planets. This is what we already have. So if we do year here, so now we have 10 times the year. That's what it would be right now. And then if you do, and let me make sure I get all my parentheses right because it will be very mad at you if you don't. We're going to do this symbol, which means it's going to divide and then it's going to get rid of the remainder. So if we take the year and divide and then get rid of the remainder, say we have 2018, then it'll go 201.8 and then it'll get rid of the remainder. So it'll be 201 and then we multiply by 10 again, 2010. So that's how we've got the decade. So we'll create that. And I've just realized I've created it without a way to look at it. So we'll go ahead and do implanets.head. Get the first 10 here. So we'll do that, and now we'll actually be able to see it. And look at that. We have a decade column, and our math worked out just right. So we have 2006 in the 2000s, 2011 in the 2010s, 96 in the 90s. Now we have a new column just like that. And you can see it's just that easy to create a new column. You do the data frame, you type anything you want in here. You could type absolutely anything, and it will create a column with that name. So next, we want to create a new column, orbital year, orbital period, currently in days, and we want that to express the orbital period in years. So does anyone have an idea of the code we might use to do that? I'll give you about a minute to think about it in the chat, and then type your answer in the chat when you think you have it. Oh, look at this. That looks wonderful. So we know we want it to be called orbital year. I believe I'm using the same code you have. Let's try it out. So without just copying pasting over, you have imp planets year. Yep. Year. Ah, okay. You wanted orbital period instead. That makes sense. And then you want it to be over 365. All right, that seems to make some sense. And now I'm going to make sure that I don't make the same mistake and make sure we can actually see it this time. And what did I do? Ah, that should be an underscore. There we go. And look at this. That seems to make some sense. 269 days seems like about 0.73 of a year. 362 days is pretty close to a year. It looks like we have created the new column exactly as we wanted. So now that we know how to do this, let's look at this assign method as the last thing that I get to teach you before I pass control back over. So first thing we can do is, there we go. Okay, so the first thing we're going to do is drop the columns we've just created. Unfortunately, they were great, but we have to get rid of them. So something we can do is in minutes dot drop. And then what does dot drop want? It wants labels. So the label is going to be the index or column labels to drop. So let's say labels equals the columns we want to drop. What did we name them? We named the first one decade, and we named the second one orbital year. All right. And now drop also, just like the other thing, it wants axis. So we'll say axis equals, and we're going to use Adam's tip again. You can just use 0 or 1, but we want to make sure we're not getting anything confused. So we're dropping columns here. So let's just say we want to drop column. And now I have to make sure that it's not, that it's column and not columns. Well, I'll let it tell me. All right. Let's look at it. It was column, wasn't it?
I think this is one of those gotchas where you can't actually run this particular cell twice. So once you drop.
Oh, yes, it is. Yep, because I dropped them. That is a shame, isn't it?
That's okay. You could just print it if planets in a different cell.
Yep. Let's just make sure that I haven't dropped too many things. Oh, look at that. We did drop them. So it did work. So now we are back to our data frame with none of the columns that we created yet, but we're going to recreate them using assign. So let's use assign to recreate our decade column. So the way we do that, imp planets again, and we're going to say it now it equals imp planets dot assign. And let's open that up and see what assign wants. It wants arguments. So what we'll input in the arguments is the same thing that it's very similar to what we were doing before. So we can say something like decade equals, and in lieu of retyping all of this and probably making a math mistake, I'm just going to copy it from up here. We'll say decade equals what we had before. So now this should, assuming I have all of my parentheses right, create that. Let's look at it. And look at that, we have decade back. So we can see that this is another method of doing exactly what we did before and creating that decade column. So now we're going to drop it again, and I'm going to do a better job of dropping this time. So we're going to do imp planets drop. The labels we want to drop is just decade this time. That needs to be in quotes, and axis equals 1, and we'll do in place equals true to make sure it stays the same. And I won't make the same mistake and double drop. So now we'll look at it again. And it's gone again. So it's just as easy as that. We can use assign to create columns. We can use drop to drop them. And now the last thing we want to do is we're going to try chaining to make a decade and a century column. This is quite a complicated function. So if you get lost, don't worry, I'll explain each piece of it. But the first thing we know is we're creating a decade column. So we already made a decade column. So let's just grab the code for that. So if we run just this, it'll create a decade column. But we also want a century column. So if we're assigning multiple columns, this first argument is decade. Let's make one for century. Century, so I can spell. There we go. Now, century is going to require another little math trick that I'll explain, but this is what it'll look like. Typing. That should do it. Let's make sure that I typed everything right and that we have a century column. All right. And I'm going to do dot head because I know there's a 90s one in there, so I can make sure it works. Perfect. So if you get lost in the math, don't worry. But what this is doing, this lambda allows us to take in the one that we've already created and work on it again. So since we're working on decade, we're doing the same math trick where we divide by 100 and get rid of the remainder and then multiply 100 to make sure we only have the first two numbers. but then the lambda is just making sure we can work on the data frame that we're just now creating. But basically we're doing the same trick, and this is a demonstration that you can create multiple columns using assign at the same time, which is a benefit over the other methods of creating columns where you have to do it one at a time, line by line, assigning it through the dictionary method. So we have an exercise here, but I think in the interest of time, I'm going to pass it back over to Dr. Bell. And if you want to go through the exercise, that's fine. Or if you'd like to move back on to transform and apply, that works too.
Yeah, I was kind of having the same thought about the time that we have. But Preston, thank you so much for that. I think you had such a great discussion about what the things are that we like to do for data analysis and how we can do them in Pandas. Let me just go ahead and share my screen.
Oh, I
had to catch up to where we were. So let's see. All right, there we go. All right, so as Preston said, we just now discussed two methods for mutating new columns. And so the first one is like super Python-y, and it's very programming. But the second way that Preston talked about, so this assign method, this one is actually very R-ish. So it's very tidyverse-ish. And so as Preston said, there's actually no way currently to create these columns at the same exact time when the second thing that you're creating, so the century, is depending on something that you created in your first statement. So this is one big chain statement. And if you were going to do this in the other way, you would actually have to mutate a column and then now use that column in a second statement that you've created in order to calculate century. So the assign method is particularly good if you want to chain together things where your following statements, so like the century, is depending on the output of the initial statements. So thank you for talking about that, Preston. All right, fantastic. Let's see, it's 12:20 essentially. Let's see. Well, maybe let's pause on just try it yourself. We'll pause on the try it yourself and go straight on into the putting things together with transform and apply. And if we have time, we'll come back to this try it yourself section. So transform and apply. So these are two really great methods. And these are great methods particularly because they allow you to do, how might I say this, for loop-like behavior in a vectorized fashion. And so again, we said that we really dislike for loops when we're working with Pandas data frames and Pandas series because the operations that we apply generally are able to be executed a little bit faster if we apply them in a vectorized format. So apply is just a little bit different. There are ways that you can kind of speed up that operation, but apply does allow you to have more of a vectorized approach to applying an arbitrary function to a particular group or a set of data. So what in the world did that even just mean? Well, let's take a look. So maybe one of our interests, so maybe we're about to do a linear or logistic regression, which would require us to normalize one or more of our columns, well, our columns which are numerical. So how could we do that? How can we do that programmatically? Because actually what we want to do is we would want to take some, for example, if we're trying to standardize the mass in particular, we would need to take the mass, so each cell of mass for each of the planets, then we would need to subtract off the mean of that entire column and then divide by the standard deviation of that entire column. So that might not be something that's built in. And if you have operations that you need to do that are not necessarily built in, you can use that lambda function, which Preston just described, to be able to apply that lambda function to each and every cell that you're interested in, or particularly the column that you're interested in. So let's see what that looks like. So we're going to create a new column, mass STD, meaning mass standardized. And so the way that we do that, as Preston says, we just say that it is so for our new data frame. So we do planets, which is the name of our data frame. And we say we're creating this new column called mass standard. then what do we need to do? Well, we need to select the mass column because that's the one that we're interested in. So we're going to take that one, select it, mass, and then we're going to apply this function called transform. And transform I tend to like a lot because transform transforms the data and then it returns it in the same shape as the input. And that's exactly what we want because we need mass standard to have the same number of columns or number of rows as in planets. So let's see, let's try transform. So we're just going to use that function. So transform. And now we need to define the transformation that we're going to apply to each of these cells. Or to this series. So let's see. Well, we know we're going to be doing some kind of anonymous function. So those are lambda functions. And we know that we're going to have to operate on something. And we'll just give it a dummy name called x. So now x is the thing that we're working on. And we said that we're trying to create or calculate we're trying to standardize this, meaning that we need to take an element, subtract the mean of that entire column, and divide by the standard deviation of the entire column. Well, thinking in a vectorized way, we can actually do that. So let's write the first little piece. So subtracting the mean. So that's not right. So I'm just going to add these two parentheses first because we're about to have to do that anyways. Actually, I should have just added. We're in just parentheses struggle. So we're just going to add one. And I'm just going to space this one out just a little bit so we can separate those. So now we're going to take x. X is the entirety of the column. It represents every cell. It's the vector x, which is mass. And we're just going to subtract off that. So the mean of that column, right? And then what we need to do with that quantity, which is why we put that parentheses in at the beginning, is we need to divide by the standard deviation of that column. So the column is x, and we need to divide by the standard deviation. All right, let's see what that produces for us. Let's see. And I'm just going to type in if planets down here so we can see that printed out a little bit. And let's see. So let's just look at this one more time. We're creating this column called mass standard. We're using the specific column of mass. And so do keep in mind that once you do this operation here, what is returned is actually a pandas series, which allows us to do some interesting operations on it, one of which is transform. And when we transform this, we're applying that to the entire series, so the entire column, which is called x. And we're going to do this anonymous function defined by lambda x, which is the vector x minus its mean divided by a standard deviation. So let's take a look at that. Oh my goodness. Wow, there's some challenging numbers there. So some of them, like in these, that's quite interesting there. Well, let's come back to that. So first, we can see this kind of situation here. So we can see that it did something. And then, so for example, this is 1.66, but it has all these decimals back behind here. So it's possible that we might actually just want to round that instead of just leaving it to be what it is. So we can actually do that here actually in the transformation as well. So we're going to divide by the standard deviation. But then we're also going to round that. And that's actually very interesting. I think we need to actually move this. So we're going to round that, and we add another parentheses, so that actually closes this function. I'm in parentheses from it's this one. Okay, so where are we right now? Where are we in the parentheses? So right now we have this one, which we want to close this, but then we want to round this entire statement right here. So let's add another parentheses. That I believe should do it for us. Okay, that looks right. This is the ending of this one, and this is the ending Woo! Parentheses struggle. All right. Woo! Now we can see that we have a little bit of better values here. Woo! Oh, but we see that we actually have done some default rounding. And maybe we want to say the decimal points that we want to actually have. So what we're going to do is go ahead and put a 2 there. So maybe we'll have 2 decimal points. And this is looking a lot better. All right, so this is believable. But now let's just take a moment and look at these down here. Because these had really crazy looking numbers. In fact, this is -0. And then, but why? So sometimes whenever you fill INACE, and sometimes when you fill INACE, particularly with the mean, it results in strange behavior if too much of your data is filled with the mean. So this right here, all of these have the same value because I believe these are the ones that are filled with the means. And then these with the, what is that value minus the mean is 0. So whenever you are doing imputation, you always need to be really careful about the amount of data that you're filling in, because in the end, it can result in very non-clear or not accurate behavior if you fill it too many. All right, let's see. So now we've learned how to use transform and how we can apply a function to a particular column. Let's see other things that we can do. So maybe we want to collapse our methods that we have. So for example, I know that you guys have gone over value counts. So let's look at the value counts in the methods again. So let's see if planets. At method. And then let's do value counts. Let's just see the number of methods that we have available here. All right, so we see here that actually the dominating ones are this radial velocity, transit, imaging, and microlensing. And these other ones down here, they're just kind of, maybe we would want to collapse them into a different category, which is other. So we can actually do that using transform. So there are other ways to do this as well. But to demonstrate how we would use transform or apply, let's see what that would look like. So the first thing that we can do is decide that we're actually the names of the ones that we're going to keep. So radial velocity, transit, imaging, and microlensing. Let's say that we want to keep these because they compose the greatest ones. So now let's just make a list of those. We're just going to keep the ones that we want. So we're just going to call that keep methods. And we're just going to type that in. We're going to type radial velocity. And again, right now, we're just creating a list of the types that we want to keep, the methods that we want to keep. So we want imaging, and we also want microlensing. Yeah, right. I think I spelled that. So now that we have that, how can we fix the methods column to change everything that is not those into other? So one way, let's just use the transform method. Maybe we were going to try to brute force this. So what we can do is we can, again, we're just going to make a new column called implanets. Or sorry, we're going to use the implanets data frame, and we're going to make a new method column called method min. And this one is just going to contain these 4 with something called other. And how can we do that? Let's see. Well, we know that we're going to be using the methods column, method column. And we know that we're probably going to need to do an operation on it, meaning that we need to transform it using some function. So we know that we can use transform because we also need to get back something that has the same shape as this particular series. Okay, so how are we going to transform this? Well, we're again going to apply our lambda method. And we're going to apply this in a vectorized way. So let's just think about this. So we're going to keep the value of x if it is in keep methods. Otherwise, we are going to return the string other. How is that going to work? Let's just think about that again. So if this value is in this, we're just going to return this because it's something we want to keep. If this value is not in this, then we're going to return other as a string, because that's going to be its new method designation. How can we write that? Well, this actually takes a little bit of knowledge about Python. And there are other ways to do this. For example, this lambda function. It's completely unnecessary to use lambda functions. We're just showing you how to do this here. But you could actually write another function. You could define another function and then pass that in here and then pass x into that function. So this is just an anonymous function. This is something that you do if you only have to do it about once. But if it's something that you need to apply in a repeated fashion, you do tend to like to define a function and then use that function. Regardless, so we said that we were going to take x. We said we're going to keep x if x is in keep methods. That's literally what we said. We said we're going to keep x if x is in this list. Otherwise, so else, we're going to return other. That's any solve. So now I'm actually going to go ahead and type out in planets. And I'm also going to go ahead and comment this line so we don't get that many things. So now let's see how that goes. Oh, ooh, on Teddy solve. All right, so we can see that method min. We can't really see if this had an effect because this clearly matches this. Those are the two that we obviously wanted to keep. So actually, let's go ahead and uncomment this one. And now we're going to do the value counts on method min. Let's see how that goes. Fantastic. So now you can see that in method min, we've done exactly what we wanted. We only kept radial velocity, transit imaging, and microlensing. And everything else has been converted to other. And again, we did that by just using this ternary operator for Python. We just said we're returning x if x is in this list. Otherwise, we're going to return other. And we applied that function using transform. So there's also another way to do this. And it looks very, very similar, especially for Panda series. But let me introduce you to the apply method. And as it were, the behavior looks absolutely identical for this particular scenario. So I just copied that. And the same type of behavior works for apply. So apply, again, is a little bit more flexible in a sense than transform. And so this just applies, as it says here, it just applies some function along an axis of a data frame. And this also applies to Panda series. And so that you can see, this actually looks completely the same. So something that I like, though, about apply is this result type, because it allows you to return things that are a little bit strange, so not in the dimensions of the original data frame, so that then you can add that onto the data frame as well. So I really do like this function, and again, it tends to be a little bit more flexible. So we can actually execute this. And why can't I just like add these things in here? Well, every time you execute this, all it does is do the same thing. So this time that it executes, it's going to look at method and it's going to transform it and create this column. This time it's going to do the same thing and it's just going to overwrite that column that we just had. And then here, we're just going to show that column. So let's see, let's run that one. And we can see it has the same exact behavior, which is awesome. But again, apply is more flexible in that there are different types of things that you're able to return instead of something that has to have the exact dimension of the input. Oh, and it looks like I accidentally, oh, no. So we can also do check to see these values in a slightly different way by using query, which is our favorite. So we can ask the data frame, okay, which ones are now other? Like which of these entries is now other? So let's see. Yep, planets. And we said that we're going to click query, and we can ask it which of the method min is equal to other. And let's see what it returns. And it tells us, indeed, we do have things that are other. All right. So what questions do you have about using applying functions to the specific elements of a data frame? All right. Well, let's move on to group by and summarize because I know this is something that we talked about during our workshop. Okay, group by, one of my favorite methods, okay, in any language. I just love it, and I don't know why I love it. It's just what's going on. So let's see, as you learned in your R course, so the group by alone doesn't really do much. All it does is kind of just add a little bit of metadata, or for Python, it does do like this subgrouping and creation of a different class. But it's hard to kind of understand that unless you look into the actual groups of the class. And so usually when you're doing a group by, you're trying to perform an operation on the group. So no one really tends to use the group by alone. You tend to use it in conjunction with another function. So let's see what that looks like. All right, so maybe we have all of these different method min types that we just discussed. And maybe we want to know how many planets there are for each method min type. So interesting, we kind of already did sort of answer that with this, but depending on the entries of your data frame, you may need to be a little bit more specific. So let's take a look at how we can answer that using group by. Well, oh my goodness. Lakia, I can never say it right. Lakia, that is looking really good. That looks like a great answer. So let's see, for within planets, he says what we want to do is group by something in particular. So what do we want to group by? The values in method min. And then, oops, didn't type that quite right. And then what do we want to do with those groups? For each group, we want to know the count of them. Let's just try that, count. Let's see how that goes. All right, so it shows us the counts of each of these different methods. But maybe if we only want a particular column, we can also find that as well. So let's see how that goes. We can do if planets again. We can group by method. Oh, wow, guys, just not doing a great job typing today. They're offset my computer. Okay, so there we go. And then let's see if we can select the method min column to return. We want to return the counts of that. All right, and we can see that this successfully returns our method min column, and this also returns the counts. So then what other kind of summarizing functionality can we apply? Can someone give me an example of another type of summarize operation, maybe that you guys did in R? So something that collapses a set of numeric values into a summarized value of that group. So like if I have a class and there was a test, like how would I try to figure out in general how people did? What operation might I do to those test values for the class? You guys are super quiet today. So I know you guys already know because you guys have been in class for like years now. But if oh, perfect. Yeah, yes. So you would take the mean. So you'd add all those things up together and divide by the sum, just like you said. So you take the mean of it. So for each group, you might want to know the mean distance for all of the different planet systems. So how in the world can we figure that out? So let's see. The planet system is actually given by this number column. And so if we want to know the mean distance for each of these individual groups by number, that's actually something that we can phrase to ourselves and type in. So let's see. I know that I want planets. And I know that, what did we say? I want to know the mean distance for the planet system. So I want to group by the system. And we know that that's given by the number column. I said I want to get the mean distance, so I select that column. And then I know that I want to get the mean. So I provide that function. So let's see how that goes. Okay, so it looks like the mean distance for the different planet systems. So these are each of the systems. And this is the mean distance for all of them. So it looks like planet system 7, super high distance, 4, maybe the smallest distance, and these other ones are somewhere in between. But this one seems to be pretty far away. And not only that, that's a very interesting number, the 780, like 780 period. That could indicate that there might be something interesting about this data that might need to be studied further. All right, so let's see. In addition, you can also group by multiple P's. So maybe you want to know the median value of the planets discovered by some particular method for a particular system. Well, the way that we could do that is very similar. And actually, I'm going to give you a moment to try that on your own. So right now, what you're going to try is, and I think I'll give you about 2 minutes, so until 12:45. Figure out if you wanted to group by the method, particularly method min, and the planet system, how would you do that? And then if you wanted to calculate the median for each of these, how would you do it? I see we have an answer in the chat, but please feel free to drop your answers in the chat as you think and decide. All right. Does anyone have any other thoughts to what Lakia said? All right. Well, I wouldn't either. Lakia had it right in mind, the perfect solution. So instead of just using the sole value here, you could pass a list of things that you want to group by using the list indicator, which is given by brackets. So how might that look? Well, we do the same thing. If planets got grouped by, and we're going to pass in the list of method min and number. And we said that we wanted the median, so we're going to apply that to each of the groups. And there we go. We got the median values for all of the grouped by method min and number. And we have all of the different columns and their medians. So you can see here, this is pretty cool that, so we can say that for imaging doesn't have any number systems of like 2 and 3, 5 and 6, but then radial velocity has number systems and discovered number systems through that method for all the systems. There's 6, there's 7. No, transit also just that method was used to discover a lot of different systems. All right, So that is a way that we can perform operations and summarizing operations on a subset of the data, or actually not a subset of the data, but on groups of the data. And we can study the data based on how similar it is to other pieces of data. All right, what questions do you have about that? All right, moving right along. So if you want to perform more expansive summarization, like you want to get a lot of different values back for a lot of different columns, the ag function is actually really great about this. So let's see what that looks like. And it's going to look very similar to what we had before with the group by and the summarize, but now instead of just saying some functions, so instead of .count or .need, we're actually going to use .ag. And we're going to pass in a list of the functions that we want to use to aggregate. So let's see what that looks like. We're going to try to find the max, median, and minimum of both mass and distance. Interesting. Oh, grouped by the method min. Okay, so in the planets, we wanted to group by method min, right? And we wanted to find those values for mass and distance. So we know we need to select those columns. And since it's more than one column, we know that we need to use a list to indicate that. So mass, distance. And we said that we wanted to apply a number of functions to each of these columns. And so we could use the ag function to do that. Well, what does that look like? Well, we again pass in a list of the functions that we want to apply. And we can either pass in strings. So like min is a string that we can use. We can pass in actual functions. So np.median, we saw that before. That's calculating the median using NumPy. Or we can pass in regular other functions provided by pandas. So let's see how this looks as a result. Well, this provides exactly what we were looking for. And I really love that Pandas has the insight to report the data frames in this way. So we said that we wanted to group by the method min, so we can see the different groups here. But here we can see the aggregations, min, median, and max, min, median, and max, for each of our columns that we were looking for. So for mass and distance. So here are all those summarized statistics for mass, and here are the summaries for distance. And this can provide a lot of great insight just in one single command, which is really, really nice. You can also provide specific types of aggregations on specific columns. So maybe for mass, you did want min, max, and median, but maybe for distance, you wanted the mean for whatever reason. Well, you can also specify that. And let's see what that looks like. I'm going to do in planets. We're going to, again, group by our method min. We still want to work on, oh, nope, we're going to be looking on something else because we're finding the total counts of the numbers column and the mean of the distance column. All right. So I read the string there, the comment. So we know that we're going to use the numbers column. And we know that we're going to use the distance column. All right. And we said that we're going to use that ag because it allows us to do more flexibility on our functionality, on our summarizing functionality. And now we need to tell it exactly what we want to do with each column. And we can do that with a dictionary. So let's use a dictionary that's indicated by these curly braces. Okay. And so I'm actually just going to click enter right now. I think that was the best idea. Yeah, I'm not going to do that. Change it. I'm going to undo that. All right, so we are going to make a dictionary, and we're going to tell it for the number column, the number column, we're going to tell it what we want it to do. We want it to find the total counts. So the function for that is called count. And then we want to say for the distance column, we're we're going to tell it the value there that we want it to do is use the main function. So let's see how that goes. All right. And you can see here that we actually perform different behaviors on the different columns based on what we specified by our aggregation dictionary. And again, what we did here is we said, hey, whenever, you know, this for this name of the column, I want you to do this operation. For this column name, I want you to do this operation. And we specified that using the dictionary. All right, so I think we have just 8 more minutes left. I think that may give us time to go through a range. A range could be really nice, and you may have to go through join on your own. But I do think that the join here is pretty good about explaining what that is like. So let's go through a range now, and then you can do join and plotting on your own. So let's see right quick. Arranging, as you recall, is just is changing the order of the data. So maybe you need something to be sorted instead of it being, you know, willy-nilly. So let's see how we can do that. Well, in R, or in the tidyverse, it's called arrange. But in Python and in Pandas, it's referred to as sorting. And sorting is more of a programming word for what we're trying to do. So we do know that we're going to be working on implanets. And maybe we want to, that's really weird.
I'm going to use sort values for this one.
That sounds good. We know that we want to sort the values. So we tell it exactly to do that. Sort values. I think it's funny. This says age. I was like, why does it say age? It's so weird. I think we want to sort according to number. So we're going to sort by exactly that, the number of our planet system. So we're just going to
I think it's just a grammar mistake in regards to age. I think somebody just put, whoever did it, put age instead of number. I don't think there's age anywhere on the planet's data. So
yeah, I think it's just a typo. So let's see how this goes. So now we sorted by number. And here we can actually see that the number actually is sorted increasingly. So we would call that it's sorted in ascending order. Maybe we don't want it to be ascending. Maybe we want to sort by descending. Well, we could do that as well using the same functionality, but using a keyword that will set that ascending to be false. So let's see what that looks like. Again, we're going to sort values. Let me scroll up a little bit. See that? There we go. We said we're sorting by number. Oh. And then let's see. It tells us here that there's some different things that we can do. One, we can do it by axis, which is very interesting. But it says here ascending equals true by default. That's the thing that we kind of want to change. So ascending, bool, or list of bool. Ooh, list of bool. That's interesting. Default is true, sort ascending versus descending. All right, so descending, we're going to specify false. So we're just going to use that, ascending equals false. See how that goes. All right, we know that we sorted by number here, and just as promised, it arranged it according to that. So now we can see that the highest number is first, and then it descends as we go. We can also sort, as we just saw, by a number of different columns. So what might that look like? Well, we do know whenever we want to do multiple things or use multiple columns, we tend to use a list. So that's no different here. We do exactly the same thing. So in planets, oops, and we're going to sort values by what? A specific list of columns. So now we're going to do maybe mass and distance. And we expect both of these to be ascending. So let's see what that looks like. So we can see that in general, the mass is increasing. And additionally, along with the distance, they are both increasing. And so something that you do see very interestingly is there is a sorting that kind of occurs between the two. And so you might feel as you look at distance that maybe like, how is this 110, this 264, this 94, how is that working? Well, it's more about the order in which you pass these in. And so these now match these. All right, let's take a look at what it is like if we want things to, so we saw before that we can sort by ascending or descending. Maybe we want mass to be ascending and distance to be descending. So let's see what that looks like. Well, it's going to be exactly what we did before. In planets, sort values by, we're passing in our list of mass and distance. And then we said we need to use the ascending key word to determine whether we want things to be ascending or descending. And we said before that when we want to specify multiple things, what is it that we use? What data structure do we use when we want to specify multiple things in Pandas? Someone said it before, and we just use a list. So now we give it a list of the Boolean values that we want to apply. So the first one will apply to this one, and the second one will apply to this one. And we could say the first one, I want it to be descending, and distance, I want it to be ascending. I think I wrote the exact opposite of that in the column, in the comment. So let's set that one to be true. This one. Let's see how that goes. Mass, ascending, distance, descending. So it's kind of hard to see. I think it might be better as if we were to try this with maybe radial. Here we can see this is going up in alphabetical order. And then with the distance, we can see that that is decreasing. So this is increasing in terms of alphabetical order. This one we can see is decreasing in numerical order. And this tends to be more clear when you're using like categorical variables, because if you can see kind of the turnover as you go along. All right, I see that it's 1 o'clock. There are some try it yourselves to do on your own. But I think that this ends our Python for Data Science workshop. Please feel free to look more deeply into these particular notebooks and learn more about what is going on with Pandas. Also, again, visit our Python for Deep Learning Intensive, which will learn more about Python itself. And also make sure to give the try it yourself exercises in this notebook a good try. I think next week we have the software development workshop, I think. And I hope to see you all there. And please feel free to email us or contact us with any questions that you have. Thanks for coming.
So, yeah, first off, I know that you're gonna need to run the code